So in this video I'm going to be talking about how to find the centroid of an area using integration. But before I actually define a centroid of an area, I'm going to talk about a concept from physics and statics in particular, which tells us that if we have a pivot point and some kind of structure hanging from it, and then we have forces that are acting at fixed points along there, and the distance between those points is defined by, say, we have a force F1 at a distance d1 from that pivot point, and then we have a force F2 at a distance d2, then these two forces are going to cause a rotation about that pivot point. So if we want the whole thing to be in equilibrium, what we need to do is we need to have another force that is going in the opposite direction. So this total force, we're going to call it F, and it should be equal to those two forces added together, because the whole system needs to be in equilibrium, which means this force needs to be equal to those two for this thing to actually be in equilibrium. And now we're going to have to place this force at some distance d. So we're going to have to place that force at some distance d. So how do we find that d? Well, we know that a moment in physics is simply a force times the perpendicular distance from the pivot point. So that means that the sum of the moments needs to be 0, because we want 0 rotation to happen along this structure. So this total force times this distance needs to be equal to F1 d1 plus F2 d2. And if we want to solve for d, then what we would have to write is 1 over f times the sum of the forces Fj dj from j equals 1 to n. If we want to make this a more general case in which we have n number of forces acting on it, then this is the formula we would have. So that's how we would find that point at which this thing is balanced out. So that's what the centroid of an area is essentially. It is a point at which an area, say an area like this, is balanced out in terms of its position in space with respect to the x and y axis. So this centroid C is defined by two coordinates, y bar and x bar and y bar, and basically it means that the area above and below it and to the left and right are all balanced, so that this thing is sort of stationary. But it's not a physical concept, it's more like a mathematical concept. But it is analogous to this concept from physics. So how can we derive an expression for the centroid of an area that is arbitrary? Well, let's start out with the following. Let's say we have some kind of area here. I'm going to draw something very generic just so that you get an idea. So let's say this whole area goes from A to B, and we have y and x, and let's say it is defined by a function that is actually two functions subtracted together, because it is going to be the area bound between a curve at the bottom and a curve at the top. So this whole function of the boundary is going to be defined by two functions subtracted together. So if we want to find the centroid of this area, C x bar y bar, what we need to do is we need to apply the same concept of balancing forces, but in this case what we're going to be balancing is areas, because we're going to take little slices. So I'm just going to change the color here a little bit. We're going to be taking small slices here. I'm gonna take another one there, and you can imagine that I'm gonna fill this whole thing with rectangles like that. So let's make the width delta x as we have defined before. Let's assume all of them have the same width, and then the height of each one is going to be, well, it's going to be the height of this. So it's going to be the height of f of x, and in general that's going to be f2 minus f1 at each point of x that we choose along that interval. So the idea is we want to balance those out with respect to the y-axis to find the x coordinate of that centroid. So this is going to be, say, x2, x1, 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 x2, the distance here is going to be x3, and so on and so on. And we're going to do the same for every single infinitesimally thin slice that we have along that area in the x direction. So in the end, to balance this out, we're going to have x bar, that's going to be at the center of the area, times the total area that is bounded by that function, is going to be equal to the following. So that's going to be equal to the sum of x times f of x. So remember, we're balancing areas out, so the area is going to be f of x times delta x. So this is the area, and the distance from the y-axis is given by x. So this here is analogous to a moment where you have f, so f would be the area and the distance would be x. So that's what we have here. So we're going to have j equals 1 n, and delta x is going to be defined as b minus a over n once again. So obviously we want to have these four continuous functions, so we need to make those infinitesimally small. And as we discussed in previous videos about the definite integral, is that we can define it as the limit of this sum, which is called a Riemann sum of some sort, as n approaches infinity. So we can rewrite the x bar coordinate as 1 over a times the integral from a to b, because that's the integral along the x-axis, of x times the function x dx. But we know that the area of this is going to be the area of f of x dx. So we can rewrite the whole thing as x bar equals to integral of ab x f of x dx, integral of ab f of x dx. And I know what you're thinking. You think, oh, maybe we can cancel out that f of x, but we can't, because this function here and this function here are completely different, so we cannot do that. Now we could use the same argument to find the coordinate y bar of the centroid, and instead of cutting slices vertically, we can cut slices horizontally and then have the distance marked from the x-axis instead. So let's have a horizontal slice, and let's have this distance is going to be y, this thickness is going to be delta y, and now the value of the function is actually going to be given as a function of y. So this value is going to be a function of y. So now we have to invert this concept. We have to invert this such that we can express x as a function of y, and that will allow us to find the center or the coordinate y bar of the centroid. So using the same, and also notice that the boundaries are going to change, the boundaries of integration, because now no longer we have a and b, but we actually have some boundary here. So we need to take into account the minimum of this function at the bottom and the maximum of this function at the top. Those are going to become the new boundaries. So I'm going to call those boundaries. Let's choose some alpha and beta. Let's have alpha and beta as those boundaries for y. So our center or coordinate for the center in the y direction is going to be integral of alpha to beta of y times f as a function of y times dy over the integral of alpha to beta of f of y times dy. So now that we have worked out those two things, we can actually proceed and apply this to an example. So I am going to erase this, and I'm going to show you an example of how we can apply this to find the center of an area. So let's also get rid of all this. And I have a little bit here which I need to get rid of. Alright, so let's have the following area. So let's have the xy plane. Let's have some straight function there, and then some function here. Let's call this x squared, and let's call this x. and we want to find the centroid of this area bound between those two curves between 0 and 1 along the x-axis. So that's the area. The centroid should be somewhere there. Alright, so we're going to find x bar first. So how do we find x bar? Well, clearly we're going to have to use x bar equals to the integral from 0 to 1 x f of x. So I'm just going to put f of x here. So what's going to be f of x? F of x is going to be the difference between the top function and the bottom function. And as we discussed in the previous video where we dealt with the area between two curves, in this case the function at the top is going to be x and the function at the bottom is going to be x squared. So we're going to have that on the numerator, and on the denominator we're going to have x minus x squared dx. So let's solve this. This is going to be equal to, that becomes x squared, so that's x cubed over 3 once we integrate, minus x cubed integrated, that's x to the power 4 over 4, 1 over 0, and this is over the total area, which is going to be x squared over 2 minus x cubed over 3, 1 0, and this is going to become 1 over 12 over 1 over 6, and this whole thing becomes 1 over 2. So that means that our coordinate for the center of this area is going to be at 0.5, so halfway through in the interval. Now what's going to be the case for y? Well, for y we need to express x as a function of y. So we're going to have to make this function equal to y. Actually, I'm going to have to redraw this diagram so that you can have a better idea of what we're dealing with here. So I'm going to put y here and x here. So if we look at it this way, we have our function x equals to y going this way, and the other function is going like this. So this is going to be x squared equals to y, which is the same as saying x equals to square root of y. So this is our function of x with respect to y as a function of y, and this is now the area. So we know this is 1, along the x-axis is 0. So what's going to be this point now? Well, because these two functions intersect at the point 1, 1, that's going to be 1. So that means that our boundaries of integration for y, in this case only, is going to be 0 to 1 as well. So let's apply that to the formula and let's find y bar. So this is going to be 0 to 1 of y times, once again we're going to have to subtract the 2. So in this case you notice that this is the function that is on the top. So that's going to be square root of y minus the function at the bottom, which is this linear equation, over the total area, which is 0 to 1 square root of y minus y dy. And you can integrate this using the methods. You know that a square root can be expressed as a power of half, so you can use basic integration on that, and in the end you will end up with the answer 2 over 5. So that means that the centroid of this particular area is going to be located at 0.5 in the x direction and 0.4 in the y direction. So this is going to be the centroid of this area. So this is one of the many things that you can do with definite integrals. And in the next video, we're actually going to be finding the volume of a solid of revolution. So that's going to be quite interesting because it is going to be drawing on the same concepts we dealt with here, but it's going to be extending it one step further into the third dimension. So that's what we will cover in the next video.